speaker is Paul Horja from, where are you now? Wien? I see. And he's going to talk about spherical functors and stability conditions.
Thanks for the invitation to speak here, and such a nice place to have a conference, of course. So I want to, as I think I said in the abstract, I want to revisit some older work and perhaps offer more modern point of view on some things about mirror symmetry in this sort of new world where people talk about sheaves of categories and things like that. So, so this is what I'm going to say today is joined with Ludmil, but it's part of a larger project with Gabriel Kerr, which should have an A side, so doesn't have yet that much of an A side, so maybe it will have an A side too. So, so let me start by just saying a few words, right? The classical, I mean here, really going back to the physics days when there was no really mathematical understanding. So, if you start with two dual reflexive polytopes in dual lattices, I guess from the physics point of view, what you're interested, if I understand correctly, so you take the polytope and these two functions, the polytopes and delta star, and the two functions w and w star, assigning just coefficients to the points of the polytope. And I think the physicists basically, their claim is that this defines some n equals 2 superconformal theory, which basically is parametrized by combinatorially. In the toric case, it's really parametrized by this data. So one way to look at it is that, just very roughly speaking, we have a point in the moduli space of complex structures on some Calabi-Yau times another point in the moduli complex structure of the mirror Calabi-Yau. So usually that's not expressed that way. As I said, the physicists, the way they express this, they talk about the Kähler moduli space of the family of delta and W. And after lots of work and of many people, these have been interpreted in the starting, I guess, in physics with Douglas and Aspinall as geometric stability conditions, and then Bridgeland gave a definition which is not exactly what the physics definition would be. So, so in a way, these would be what I guess the physics would call the geometric stability conditions. So let me make this a little bit more precise. So usually the way this is done, you build the two associated reflexive Gorenstein cones, and sigma sigma star, and then you take the associated Gorenstein varieties, and these are going to be mirror Gorenstein varieties, pretty singular, x and x star, but they have trivial canonical bundle. And then one looks at inside at the Calabi-Yau hypersurfaces, S and S star. So one way to view, to write down a mirror symmetry statement, again, this is a little naive, would be that you can, the bounded derived category of singularity associated to xw is isomorphic to the Fukaya-Seidel category associated with x star, w star, and then of course that the DBS, the bounded derived category of coherent sheaves, is isomorphic with the Fukaya of a star. So there, as I said, this is pretty naive, This has been done by lots of people, of course, in the more classical case of Calabi-Yau's in lots of contexts. It has been extended to the non-reflexive case, and Ludmil with Mark Rose and Helge Ruda, they wrote down a clear statement what mirror symmetry should do, and then for some, I guess, Paul Seidel and Efimov, they extended this for the case of higher genus curves. So when S is, or S star rather, is a higher genus curve, you can still make a statement. So what has happening in those cases, and this is important, is that the mirror picture would somehow lead to the consideration of some perverse structure. So we don't get necessarily something which is nice and smooth, but you get some perverse structure associated with something which is singular. Yes, is that a problem with my slide or with the file maybe? So let me now review some old work that I did with Lev Borisov. So there were no perverse sheaves of categories then. So basically what we wanted to do, we wanted to use mirror symmetry to connect the two sides of the story. So on one hand, you have this x sigma prime, some birational geometry associated to, say, so this to some kind of variation in the Kähler moduli space, so that P1 is supposed to be either in the moduli, the complex moduli space, or the Kähler moduli space, depending on what you're doing. And it is known that x sigma and x sigma prime are related by a Fourier-Mukai functor. So if they're kind of neighbors, this is going to be one of these generalized flops. I'm ignoring here some details, namely that even in the Tori case, you have to enhance this picture so that you work in the world of the Riemann for stacks. Otherwise, things don't work out. And then using mirror symmetry, you sort of Tori mirror symmetry, where you have this technology of Gelfand, Kasparov, and Selevinsky, you can actually study periods and write them down explicitly using the GKZ machinery, and they are these generalized hypergeometric functions. So what we did was to actually show that this diagram basically is commutative when we're talking about one of these generalized flops. So somehow we're staying kind of close in the moduli space, but of course you can extend this picture further. So I should say that Gabe actually in his talk, he mentioned this, that this can be of course extended, and you use the mechanism to kind of understand the derived category or the Fukaya category by moving along in this moduli space.
So just so I understand the picture, the idea is you have like a VGIT here, you have x delta on one side, x delta prime, sorry, x sigma on one side, x sigma prime on the other, and
right.
then in that picture there, the point is where the flop happens?
Well, you would like to think, in fact, what's going to happen in the modular, there will be a wall of codimension 1 that you can go around, in fact.
Right.
So that's what Bridgeland space is supposed to do sometimes. So. But if you write down the differential equation, what you're going to see that in such a curve you really have a point there where things go wrong. So now such a flop, in this case, induces actually two spherical functors. There is no, unfortunately, I think my slide, there's nothing to do here, I believe, right? Yep, nothing to do there. So there is a Z missing downstairs there. So I'll say a bit more about these functors. These are the so-called easy functors. And so the way indeed, so this is related a bit with the question. So the way one should think about this easy functor or this spherical functor is exactly this issue about what happens when you hit the wall. So yes, we have the same issue. All right, so let me write down an example, just one that everybody knows. So let's take the fan of P2 and the polytope of P2, the dual reflexive polytope. Let's write down the superpotential. I can write it in the torus coordinates. So the naive, as I said, very naive point of view is that you parameterize this by using the coefficients AIs, and so we define the discriminant associated to this combinatorial data to all these AIs such that there is one point in the torus where the function that's derivatives vanish. So it's easy to see that so since basically taking an AI on the discriminant corresponds to taking a hyperplane section which is singular, that the projective dual, so this is classical projective dual of X sigma is the discriminant. So basically mirror symmetry then would tell us that the Fukaya category of S is isomorphic to the equivalent to the derived category of coherent sheaves on S star, and that sits inside in this toric derived category. So somehow using so if you think about, we can think also, as I said, right on the first slide, these coefficients can be thought of as stability conditions in this very naive way. So that's what I want to do now here. I want to kind of turn tables a little bit and think about the AIs as parametrizing stability conditions in this, or in other words, the scalar moduli space for either dB S star or dB of X sigma. So the vague conjecture would be something like this, that there exists, so what do I mean by a sheaf of categories? There is some sheaf of categories. So on the moduli space, there is a local system of categories which is locally constant away from the discriminant locus. Interesting stuff is going on here too, because if you can do birational geometry, and then the T structure is going to change. So that corresponds exactly to changing the stability condition a la Bridgeland. But then when you approach the discriminant locus, these are given by, as I said, by spherical functors. And this idea is just based on intuition, as I said, gained by doing these calculations. I should say this is a little bit connected to what Carlo was saying, if I understood correctly at the end. So along the discriminant locus, in fact, they're also moving along that, some T structure is going to change. So even there is some birational geometry going on. Of course, a little harder to understand. So Now let me just very briefly say a few words about discriminant, about spherical functors. So this is a notion, I guess the abstract notion, first written down by Anno and then worked out in detail by Anno and Logvinenko. So you have two categories, and functor from S to D, which have right adjoints with the property that the natural cone with left and right adjoints with the property that the cone that you consider, the natural cone, is an equivalence of the category D. And then there is also some other technical condition that I won't discuss now. So then Kapranov and Sheckman, they made this observation, the fact that in the theory of constructible sheaves or D modules, in fact, there is an analogous notion when one talks about the two functors, I guess Delign's functors, the nearby cycle and the vanishing cycle. So, so in our context, I guess the more appropriate analogy would be with the construction of Kashivara and Mekbut-Shapira of the functors, nearby functors, the nearby cycle functor. It's a little improper name, but I think they mentioned that and they want to keep it, and the vanishing cycle functor on D module. So whenever you have y being the fiber at 0 of some analytic function, you can define, and you have a D module on X, you can define these two D modules defined by the nearby and the vanishing functor. So one word, this is also connected with some other talk here. This actually, the construction of this uses the so-called B-filtration, so which is it's based on that. So let me just again quickly give some examples of spherical functors that are well known. So this first one that shows up in the paper of Seidel and Thomas, I guess. So you have a pre-triangulated category, and an object is spherical if basically it has only two cohomology, non-vanishing cohomology, and there is some non-degenerate condition. And then the associated, so you can think about this as the case when Z is just a point. The other, for example, if X is a smooth projective Calabi-Yau, then OX is spherical. The other example, which is a little ridiculous, but it can be treated in this way, if you have a smooth divisor, then actually I star is also spherical by a little algebraic trick there. So so now I would like to make this analogy more than an analogy between spherical functors and the constructible or D module context. So about maybe 20, 30 years ago, I believe Galigo, Granger, Maisonneuve gave a equivalent description of the category of perverse sheaves on Cn with respect to the stratification of basically the x1 times x2 times xn equals 0. So I just wrote the strata there explicitly. But basically what they written down is exactly a nice algebra description, so that the category of perverse sheaves on the Cn with this stratification is given by these 2 to the n finite dimensional vector spaces and the maps between them. And the important one, in a way, is the one that sort of rings very similarly to the idea of a spherical functor. So for anyone who has been looking at mirror symmetry, this should immediately kind of bring to mind this picture in the context of the so-called large complex or large radius point. So basically, this is a point where the monodromy is in the moduli space, where the monodromy is maximally unipotent, and the structure is that you have a bunch of divisors that intersect transversely, and going around in divisors are going to be exactly spherical functors. So this is, for all intents and purposes, is the exact analog of this, as I said, 30-year-old result. So, yeah. So now, let's see. Maybe I'll go a little faster. So there is. So, you know, in principle, what one would like to do is generalize this picture to any toric variety and write down all the view all the possible components of the discriminant locus and the correspondence with spherical functors. So this hasn't been done as far as I know yet, but the combinatorics is pretty clear. So, basically, let me just say briefly what I mean here. So the GKC machinery has this nice feature that it produces what's called the secondary polytope, which is a convex polytope, a regular convex polytope with the property that any face corresponds to a polyhedral subdivision of the initial set that we studied. So there is, and these lattices are really isomorphic. So it's a nice correspondence. Of course, from our point of view, of course, what's interesting is that these the vertices determine exactly these birational toric dilemma for stacks. The toric subdivisions, they're not quite toric dilemma for stack. In fact, sometimes they're only RT stacks. However, there is a general conjecture that for each face of the secondary polytope, we should be able to associate a spherical functor using the combinatorics exactly as in the previous picture. So E would play the role of the exception locus, and Z is as before. So I cannot prove the conjecture in general, but I know what to do in the case of Lorentz toric varieties. These are not so well known by people who do toric geometry in general. They're known by people who do hyperkähler toric geometry. So I would like to maybe say just a few words about this. But the good thing about this is that you really can say anything you want to with very high precision using the combinatorial data. So let me just say a few words about what are these toric varieties, how are they built. So there is the Lorentz construction in combinatorics is basically you start with a bunch of vectors and in a lattice dimension D, and then you associate this Lorentz transform, I believe it's called. So so if you start with n elements, you associate 2 n elements to it. And the good thing about it, I mean, there are many good things about this, taking the convex hull of this new set. But one of them is that it's actually a polytope, a D plus 1, n minus 1 polytope included in a hyperplane. And the vertices, there are no vertices, so to speak, inside. So any elements that you might have had in the beginning in the set B, which are not vertices, now after this they become vertices. So, and of course now we can just run the whole program for this type of toric variety, Lorentz toric variety. So So some good things. So these are intimately related to zonotopes. So some results here. So for example, something that is not true. I mean, it's harder to compute is that in this case you can compute the rank of the K0 as the volume of some zonotope. And the most important thing from as far as you're concerned is that for this type of toric variety, there is we can write down a tilting generator made out of line bundles, basically, where by taking this alpha inside the zonotope. So again, I don't want to. And as I said, using this machinery for this case allows us to really construct the spherical functor combinatorially. In a way, it's not a very interesting case if you write down the hypergeometric system is nice, too nice in a way. But as I said, that's the only case that at least I am aware of being able to classify these spherical functors, which should arise naturally. So another toric example. Let me take let's take a very simple example. So just take n points on a segment, right? And the mirror of this is going to be, if I call this cone sigma, the sigma star is going to be a cone where to which you associate, I guess I called it x tilde, I should have said x tilde, x star. So this is the usual Kleinian and singularity. And then if you look at the superpotential, in this case, it's really, and you try to understand the discriminant, basically what you're trying to do is trying to understand the classical problem of the discriminant of a polynomial. So I called it delta. There is an issue which turns out to be quite important here, but I'll skip over it, that the GKC discriminant has some extra coefficients there. And of course, the remark that I made earlier, that this discriminant, in fact, is the classical projective dual of our variety x sigma. So there is an old result of Dinka and Rosciano from 1984, which basically where they show, maybe this is written somewhere else too, they show that one can write down, if one uses the usual stratification by the multiplicity of the singular locus, actually that stratification coincides with this stratification that I wrote down there, the locus of polynomial with high distinct roots. And what they show is that this is Whitney regular. So of course now our S here, if we look at the S, so it's not Calabi-Yau anymore, it's zero dimensional. It's basically a collection of n points, and it's the associated category. The interesting thing here, if there is anything interesting, is that one can actually sort of try to play birational geometry and write down a family of spherical functors exactly corresponding to this stratification given by Dinka and Rosciano, which is, as I said, the classical stratification. Actually, understanding exactly what these strata are is not an easy problem, and if you just Google it, there are lots of people doing all sorts of things, but it is very classical. But it's pretty difficult, and of course, they're also in the 80s, Arnold and Giventhal had some nice results about this. So anyways, the spherical, if you look at this diagram, it's sort of exactly suggestive of this, of having some kind of exceptional locus which collapses, and then that produces the spherical functor. So of course it's a little, as I said, easy because everything is in 0 dimensions. So the other interesting thing here, if you play around with these and you draw some strands, you actually can produce the expected Dn, the braid group action that you expect. So the example actually has, surprisingly, has even more geometry here. If you look at the associated secondary polytope, then that brings even, and try to understand the birational geometry of those transformations, that it's an extra layer here, which I haven't discussed, but it's kind of interlaced with this, with this family of spherical functors. All right, so at least the toric picture that is expected is a sort of a generalization of the picture that I described in the beginning. So basically, it's the analog. The idea would be that the analog of a spherical functor corresponding to one of these generalized flops, the mirror of that in this context is given by through this construction of Kashibara and McBoot-Shapira by considering the nearby and vanishing cycles. And such a picture is associated to, as I said, to a toric flop. And of course, there is the interesting question, what is the dB analog of the V structure that, as I said, is essential? What's the birational dB analog? And there, Ludmil has some ideas about this. He has a construction of something that's called categorical multiplier ideal sheaves. It's also in a way related with the perverse curve, the perverse structure that Bridgeland constructs in his proof for the threefold case, but it's not clear to me right now. So one more thing, one could try to imagine that this, of course, something like this should work in a much more general context, not necessarily toric, and some examples should be accessible to at least calculations. So one can imagine that you define a perverse sheaf of categories with stability conditions, and what happens is that along when you approach the discriminant, the stability D module degenerates in a compatible way as it happens in the toric case. All right, thank you very much.
We've got time for one question.
You know the notion of a p-factor,
Yeah.
which has been sort of talking about. So when you sort of look at the flops with sort of more complicated geometry, for example, Mukai flops, there this sort of equivalence is given by sort of p-factor construction.
Yeah.
We don't know at the moment. So how would this sort of, would you expect?
Well, I think
p-factors
what's going to happen in the general picture, there is the notion of the spherical functor will have to be sort of adjusted, so to speak, on both sides. So in other words, what I haven't said, these discriminant components come up with some multiplicities, even in the toric case, just plain toric, and the multiplicities will play an important role in actually defining this spherical functor. So maybe, as I said, my conjecture, the way I stated it there, has to be adjusted. So, but that's why it's a conjecture, but I'm not sure. So.
Thank you, speaker again.